Good morning, good afternoon, good evening, wherever you're at. Hope you are doing wonderful. What we're about to do is we're going to get right into the simplifying the radical expressions like we did the other day. This will be the second round of what we're going to be working with. But I want to make sure that you fully understand what we're doing. Now again, remember, the stuff that we're doing on this worksheet is more elaborate, more detailed than probably anything I'm going to ask you to do this year. But also remember where I pulled these problems from. I pulled them from an Algebra 1 textbook. So just something to keep in mind that these are things that you should know and are going to need to know as we move forward. All right, so there are certain problems that I want to work on with you guys from this worksheet here, and then you're going to finish up the rest of them for me. And so starting with numbers 3, 4, and 5, you can go ahead and star or circle those 3, 4, and 5, 7, 11, and 12. Okay, those are the problems I want to work on from the front side. From the back side, numbers 13, 15, 16, and 17. Now, if you turn back to the front side with me, you're going to need a calculator today. If you don't already have one, you want to get that. And we're just going to jump right into things. We want to remember the 3 rules that we talked about yesterday, which are you can have no perfect squares underneath the radical. That's the first one, okay, other than 1. So no perfect squares under the radical. You can have no radical expression in the denominator. And you can also have no fraction underneath the radical. And so keeping those 3 in mind, that's what's going to guide us as we work through these problems today. So as you look at number 3 right here, you know, we've talked about in the past how the square and square root cancel each other out. And so the question is the answer to this going to be 1? Okay? Because, you know, that would be the square and the square root canceling each other out. The easiest way to figure that out is just to work it out by hand. Okay? And so if I work this out, what's 5 squared? Well, that's 25. And what's 4 squared? Well, that's 16. And if we plug this into our calculator or just think about it, what's the square root of 25? That's 5. What's the square root of 16? That's 4. And you know what? You were right. The answer to number 3 is 1. Okay? So whenever you have a square and a square root, they cancel each other out. Now, the reason why I'm having you work on number 4 with me is because I can see a lot of people putting in their answer. The answer is going to be 4. 10 minus 6 is 4. Well, again, let's work this out and see if that answer ends up being 4. Okay? Well, 10 squared, we know 10 times 10 is 100. And 6 squared is 6 times 6, which is 36. Now, the difference between those two is 64. And if you think to yourself, what's the square root of 64? We should have 8. Okay? All right. Now you'll notice the answer here is twice the answer there. That is just by coincidence. It doesn't normally happen that way. All right? And so what I'm trying to tell you is this. If you have one term that's being squared and square rooted, they can cancel each other out. One term being squared and square rooted, cancel each other out. If you have 2 terms, like this one, we can't cancel them out. We actually have to work it out to get our answer. Okay? And so that's just something to think about there. All right, now, if we look at number 5, I got the square root of 576. That's a big number. I really won't want to have to do a whole lot of work with this one. And so the first thing I'm going to reach for is my calculator. Reach for my calculator. I type that in. And is it a perfect square? If it's a whole number, it is. And we see that that's going to be 24. Okay? And so the square root of 576 is just 24. You could also work it out like this. 24 times 24 is 576. The duplicate comes out from underneath the radical, and that's how we get the 24. Okay? So as I look at number 6 real quickly, we're not going to do this one together, but we've got big numbers right here, here and here. Okay, and remember yesterday we took these radicals and separated them, and then we simplified the radicals from there. Well, the problem is this. If I have a big number, that can be kind of labor intensive. That's a lot of work. So what I'm probably going to do is type the square root of 361 in my calculator and see if it's a perfect square. Same thing with 2,304. If it is, I'm pretty much done. If it's not, then I've got a lot of work to do. Okay, so just a hint there for number 6. All right, now moving on down the row here, we have number 7 to do next. Now number 7, I want you to write this out, remembering that we treat radical expressions like variables. I want you to write this out for me. 6x minus 5x plus 3x. Now you guys have been doing that for probably at least the last 2 years. If I add those three together, I get 6 minus 5, that's 1, plus 3, that's 4. So my answer is 4x. So the question then becomes, as I look back at my initial problem, if I have 6 radical 17 minus 5 radical 17 plus 3 radical 17, what would the answer be? Well, treat these all like x's. This is going to be 4 radical 17. Okay? All right? So again, treat the variable or the radicals like x's. All right, now what's the next one we have? Number 11, right? Yeah, okay. Looking at number 11, here's what I see. I've got a radical underneath I got a fraction underneath this radical. I have to get rid of that. So the first thing I'm going to do, since I have a fraction over here, I'm going to convert that into a fraction there. Okay? Now as I write that down, 55, what are the factors of 55? Well, 5 and 11, right? 5 times 11 is 55. 5's prime, nothing else goes into it other than 1. And 11's prime, nothing else goes into it, just 1. So there's no perfect squares in 55. So I'm going to go ahead and write down square root of 55 over 1. Minus, now I'm going to break this radical up here. 5's prime, so there's no perfect squares in that one. And 11's prime, no perfect squares in that one. Now, I've gotten rid of the fraction with the fraction underneath the radical, but I still have a radical in the denominator. So what am I going to do? Well, if you remember from the other day, we're going to rationalize this denominator, multiplying by radical 11 over radical 11. Okay? And so what that gives me is this. Radical 55 over 1, that's this first fraction here, minus 7. Now, I can multiply that by the 1 right there. 7 times 1, multiplying like times like. And radical 5 times radical 11, radical 55. All that's over radical 11 times radical 11, which is just 11. Remember, radical 11 times radical 11 is actually the square root of 121. But what's the square root of 121? It's 11. So anytime you have two numbers that are the same underneath the radical, you can go ahead and pull out the radical or just give me the number. Okay? Now the question becomes, in order to subtract these fractions, I have to have what? I have to have a common denominator. So the common denominator can often be found by multiplying these two together. So I'm going to go ahead and multiply 11 times 1, and I get 11. That's my common denominator. Now, since the denominator didn't change, the numerator doesn't change either. Okay? Over here, I increased this denominator 11 times. So I have to multiply this by 11. Now, a lot of students struggled with this when we've talked about it in the past. So I'm going to treat radical 55 like x. And if I multiply radical 55 by x, I get 11x. Okay? Excuse me, my phone is ringing here. I'll be back in 1 second. All right, I'm back. Sorry about the interruption there. My wife was calling about the grocery list later on today. Had to get that taken care of. Anyways, so yeah, I'm back to saying that treat this x like radical 55. And so when we multiply 11 times x, we know it's 11x. So what's 11 times this? Don't make it more complicated than it has to be. 11 radical 55. Okay? From there, we're going to subtract these two. So again, treating this like a variable, 11x minus 7x will give us 4x. So what is 11 radical 55 minus 7 radical 55? Well, that's 4 radical 55 over 11. Okay? Now, there's two things I would probably check from here just to make sure. I would check to make sure that there are no perfect squares in radical 55, and we've already discussed that. And I would also make sure that I can't reduce 4/11ths, which, 11 is prime, so it cannot be reduced. And so you can either leave it like that or like this. But though that's supposed to be a 55, sorry about that. That's the answer to that one there. Okay. Moving on to number 12, I'm going to start out very similar to the last one in the fact that I've got two fractions underneath the radicals. So I'm going to break this apart. Now, as I write this down, radical 5, the square root of 5, are there any perfect squares in 5? No, because 5 is prime. I cannot factor out anything from it. What about 6? Well, 6 can be broken down into 2 and 3, but there's no duplicates. There's no perfect square. So I'm going to write it just like this. Okay? Minus, and I'm going to do the same thing with 3. That's prime. 10, well, that can be broken down to 5 and 2, but again, no duplicates, just like that. Okay? Now, as I look at this, I probably should have written this a little bit differently. I want to leave a little more space here because I'm going to head into the next step that I'm going to do. So I'm going to leave a space there, and then we got this. Okay? Now, from that point, I look at the radicals in the denominator, and I think, I can't have that. So I'm thinking to myself, I want to get rid of those. I'm going to probably rationalize both denominators. This one, I'm going to multiply by radical 6 over radical 6. Remember, to rationalize, you need to multiply by whatever's in the denominator. On the other one, I'm going to go ahead and rationalize it by multiplying it by radical 10 over radical 10. Okay? Now what that's going to give me is this. For this one over here, again, you can always put a 1 in front of this if it makes you feel more comfortable, and multiply like with like. 4 times 1 is 4. Radical 5 times radical 6 is radical 30. Now, what you might want to do at this point is think to yourself, can I factor anything out of radical 30? Well, if you think about it, 5 can't be broken down, and 6 can be broken down into 2 and 3, but again, we don't have any duplicates, okay? Maybe I should write that out up here to make sure you see all that. Radical 30 becomes 5 times 6, and you can see there's no duplicates, so radical 30 is the simplified form. I can't break it down any more simple than that, okay? What's radical 6 times radical 6? Well, that would be the square root of 36, which becomes 6, okay? Now, for my other fraction, you've got radical 3 times radical 10, which is, again, radical 30. And then you've got radical 10 times radical 10, which is going to end up becoming just 10. Square root of 100 becomes 10. All right? Now, from that point, I would probably ask myself, what's the common denominator here? Because I want to subtract these two fractions. What's the common denominator? Well, the common denominator is going to be, I know a lot of you might be thinking 60, because 10 times 6, but I want the smallest number that goes into both these. So the smallest number that both these numbers go into is going to be 30. Okay? Now, to get this number here, I know that 6 times 5 is 30. So I have to multiply this times 5. Now, if you think about it, what would this be? It'd be 20x, right? So this right here multiplied by 5 would be 20 radical 30. Okay? In the other fraction, 10 times 3 is 30. So if I multiply this by 3, it's just going to be 3 radical 30. Okay? So again, I hope that's starting to click as far as how to treat the radicals, treated like the variables that we've already become very familiar with. Okay? Now in the end, I end up with 20x minus 3x. 20 radical 3 minus 3 radical 3. That's 17x, or 17 radical 30. Okay? Over 30. Okay? Now, I know I just said this like 2 minutes ago, but I want to make sure everybody's got this. I still check two things on this fraction. One, can I simplify this radical? And we already proved up here that we can't. 2, can I reduce the fraction 17/30ths? 17's prime, so I can't do that either. So another way to write this, if you see it written differently, in a textbook or something like that is that right there, 17/30 radical 30. Okay? All right, let's move on to the back side now and look at a couple more practice problems, starting with number 13 then. Okay? Now you'll notice number 13 looks very similar to the one that we did yesterday. And I know that you guys know how to distribute, and that's what you should be thinking right now if you're not. But the one reason why I wanted to do this problem is because of this right here. What number is that there? And the number is 1. Okay? So when I distribute the 5 radical 3 into the parentheses, I want to multiply like with like, and like with like. So this is going to end up being 5 times 1, which is 5, and radical 3 times radical 6, which is radical 18. Now, what I would do, instead of writing down radical 18, I would probably start to break this apart and see if there's anything that will factor out of it. So I know I've got 3 times 6, right? Radical 18 is 3 times 6. Radical 3 times radical 6. So if I break apart the 6, here's my 3 that came from that one. If I break apart the 6, 3 times 2, what's 3 times 3 times 2? It's 18, okay? So instead of writing down the number, I can just break down the two numbers that multiply together to get that number. Now this right here comes out as just a 3, and it's multiplied. Remember, anything that's inside, if it's multiplied, comes out and it's multiplied. So this is going to be 15 radical 2, okay? If I multiply like with like again, 5 times 2, that's 10. Radical 3 times radical 8, that's radical 24. Now, again, I would probably break that apart to see what we have. 3 times 8 is 24. 8 can be broken down into 2 times 4, and 4 can be broken down into 2 times 2. Now, I'd get in the habit of double checking to make sure I broke it down correctly by multiplying these back together. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. I know I've done it correctly. Okay? Now, if I look here, I see that I've got a duplicate. I've got a perfect square. That perfect square comes out just as a 2. Again, it's multiplied. So this is plus 20 radical 6, bringing the 3 and the 2 back together. Okay? Now, can I combine those? If you're thinking yes, then you need to write this down. 15x plus 20y. You wouldn't have combined these two, so why would you combine these two? And that's how I'm going to put it. Radical 2 is not the same thing as radical 6. Okay? Now, that process of multiplication that we saw in number 13 is also present in 15, in the fact that we want to multiply like with like. Now, if I do that, I get 4 times 3, which is 12, and then I'm going to put my radical down. Now, a squared isn't multiplied by any a's over here. So I'm going to write down a squared like this. Okay? And then I get b times b, which we know to be b squared, but instead of writing down b squared, I'm going to write it down like this for right now. Okay? Now, I hope you're starting to figure out what the final answer should be, because with the duplicate of a, that just comes out as a. The duplicate of b, that just comes out as b. So this is actually 12ab, and you're done. That's the simplified form. Notice again that 12 is multiplied by a and by b. The multiplication holds true whether it's under the radical or outside the radical. Okay? All right, now to finish things up, let's go to number 16 here. Okay? And I'm going to try to break apart the factors in 49 and then x to the third. So in order to do that, I know that 49 can be broken down into 7 times 7, and then x to the third can be broken down like that. Okay? If I do 16, 16 can be broken down into 4 times 4, and then x to the fifth can be written like that. Okay? 5x is there, multiplied makes it x to the fifth. So, if I go ahead and look at my duplicates, my perfect squares, the 7s will come out as a 7. So 7 times 2 is 14. And the perfect square of x will come out as just an x. Now you'll notice there that we have an x left over, so it's going to be radical x. For the other one, perfect square of 4 comes out, or perfect square of 16 comes out as a 4. So 4 times 3 is 12. I've got a perfect square of x, perfect square of x. So x times x is x squared, radical x. Now, a lot of times I want to ask students after this, can we combine those two? Are they like terms? And here's the difference between these two. Okay, you see that right there? X to the first power, x to the second power. Can't combine them, they're not like terms, so we leave them completely separate. Okay? All right, almost done. Let's go ahead and do this last problem here. Okay? And we have number 17. And you know how we talked about the the squares and the square roots canceling each other out? Well, can we do that here? Can we cancel those two out? Now, what I would encourage you to do is go back to the front side and look at number 4. Okay? Number 4 looks a lot like number 17, because we've got two terms, both of them being squared. And so I hope that you're understanding that number 4, we couldn't cancel out the square and square roots. So in number 17, we can't cancel them out either. So what I'm going to do here is this. I have to be able to bring these two terms together first before I can cancel out the square and the square root. Okay? So how do I bring them together? Well, I'm going to find a common denominator. So if you think about it, 16 times 25, that's going to be 400. Now you might not know it yet. You can go ahead and type that in, the square root of 400. You might not know it, but that's a good number. Because as you're probably finding out if you're using your calculator, that's a perfect square. Okay? In fact, let me share something with you guys that I learned a couple years ago. There's a way to figure out some of these bigger numbers if they're of the hundreds. And what I mean by that is this. You guys all know the square root of 100 is 10, right? 10 times 10 is 100. Well, the square root of 400, as you just found out, was 20. 20 times 20 is 400. If I take 30 times 30, 30 squared, you're going to get 900. If I take 40 times 40, 40 squared, that's 1600. Are you starting to see the pattern there? 50 times 50 is 2500. Notice I take the 5 and square it, 25, and then add 100. If I do 60 times 60, that would be 3600. Okay? So again, just something, if you can remember, it'll make things nice and easy for you. All right, so if I change this to 400, multiplying 16 times 25, okay, the numerator, if this denominator is multiplied by 25, the numerator has to be multiplied by 25 as well. So we get that right there. Multiplying this one by 16, I'll multiply the numerator by 16. We get that right there. Now, if we bring those two together, here's what we get. 25 plus 16, that's 41, x squared. Okay? Now, we still have a fraction underneath the radical. So I'm going to break apart that fraction and write it like this. There's 41x squared, and there's 400. Okay? Now you guys already told me the square root of 400 was 20, right? So I'm going to write that down. How would I simplify this part up here? Well, 41, I believe, is prime. I can't think of any numbers that would go into 41 evenly. But what you're going to find out is that there's no perfect squares in 41. As far as the x times x, that's just going to come out as an x. And there is your final answer. Okay? So again, I hope all that made sense. If it didn't, come and see me. Let's talk about it. But I would like you to attempt the rest of those problems there. And make sure you show me so that I can give you credit for that. Thank you so much for listening. I hope you have a great evening. And I will see you later. Good night.